Okay, I think we should get started. So welcome everyone. This is the second of the AAS sessions that are forming the meeting in a meeting on supermassive black holes with supermassive black hole studies with the legacy survey of space and time. In this session, we're going to have three talks. First, we will hear from Michael Strauss about active galaxy science with Hyper Suprime-Cam and lessons for the Rubin Observatory LSST. Then we will hear from Qingling Ni, who will tell us about the XMM-SERVS X-ray survey of the LSST deep drilling fields. And then third, we will hear from Maurizio Paolillo, who will tell us about AGN detection and characterization through optical variability and the lessons learned from the VST supernova surveys. Each talk will be about 20 minutes with 10 minutes for questions and discussion. And I will remind everyone that we are all following the AAS Code of Conduct. And we are also, as is standard for these sessions, being recorded. This is so we can share this information in the future with people who aren't able to be here today. Finally, I will just say that questions after each talk are strongly encouraged, and you can submit questions using the Q&A button down at the bottom. And please, it's better to use that Q&A button instead of the chat button. In fact, the chat button may be inaccessible to you. So please use that Q&A button to submit your questions. Again, we strongly want questions, and we budgeted a good amount of time for them. So without any further ado, we will get started. Go ahead, Michael.
Hey, thank you very much. I imagine people can hear me. It's a privilege to talk to you about AGN Science with the Hyper Suprime-Cam. And really the lesson here is that Hyper Suprime-Cam is in many ways a precursor to LSST and has some important lessons and things for us to think about as we go ahead and think about what LSST can do. Whoops. So until the Rubin Observatory is completed, the Subaru 8.2 meter telescope has the distinction of having the largest field of view of any telescope of its size, and I'll quantify that in a bit. Of its size, referring to the primary mirror, the 8.2 meters. I will mostly talk about Hyper Suprime-Cam here, or HSC, but there's another instrument, a spectrograph on the way, which, if I have time, I'll talk about, called the Prime Focus Spectrograph. And in some ways, it's doing SDSS-like surveys in a much bigger telescope. And I will just mention that the joint project of Hyper Suprime-Cam and Prime Focus Spectrograph has this rather convoluted acronym, Subaru Measurements of Images and Redshifts, which spells out sumire, which is the Japanese word for the flower violet, which you can see there. Let's go on. So let's start and describe Hyper Suprime-Cam. It's a wide field imaging camera on the Subaru telescope. Wide field, there's 1.77 degrees squared. You can see the focal plane with all the CCDs in the upper right. The left is the 3-ton, 3-meter tall wide field corrector that gives you good images across the entire field. And the lower right, you can see the team that has built it actually at the Subaru control room. So 1.77 square degrees is an impressive number. Of course, it's smaller than the 9.6 square degrees that the Rubin Observatory will have, but it's getting there. So with Hyper Suprime-Cam, we're part of a consortium that is carrying out a 330-night survey in a series of filters. I'll show you the filter traces in just a moment, covering what at the end will be just over 1,000 square degrees to about R of 26. And we have two deeper, it's a layered survey, as these things often are, a 28 square degree survey to R of 27 and 3.5 square degrees to R of 28. And that last number is comparable, or actually even a little deeper than the full 10-year depth of the Rubin Observatory. And the survey started in 2014. We're nearing the end. We should finish next year. And like everything else, it has been slowed down by COVID, but it is going forward. So I mentioned the filters GRIZY. It's a very similar filter set to LSST, but you'll notice that there is no U-band, and that is an important distinction. We also have, and I won't have time to talk about, narrowband filters that will be observed in the deep fields where we're going a little bit deeper. And again, I unfortunately will not have time to talk about that. So here's a dramatic picture of Jill Knapp, Ed Turner, and myself at Princeton with an image in the back that is actually, we took an area of 1/3 of a square degree, printed it up and printed it and put it against a wall, which is 20 feet by 8 feet. And that's what we're standing in front of. That was not done electronically. We are literally standing in front of that. And it's a truly impressive sight. And that image, which indeed comes from one of those ultra deep fields actually in Cosmos, is just about at LSST depths, and it really sort of tells us what LSST is like. Again, to experience that in full glory, you need to print it out at 20 feet by 8 feet, and that represents 1/60,000th of the full LSST survey area. So it gives you some sense of just the data stream that we're about to have. So here's another view of that image now shown electronically. This is a GRI color composite, and there's 250,000 detected objects. I'll let you count to check me on that number. And again, I wanted to just give a sense of just how deep those data go. Here's a small chunk over on the left-hand side of that previous picture. That's about 0.2 degrees on a side. If you just keep on zooming in, you get a sense of just how rich the sky is in galaxies. And it's not literally true that everything that we see is a galaxy, but the vast majority of the objects, certainly at the faint end, are galaxies. Let me just take one more. Now we're looking at a few arc minutes at the side, and you see that the number density of galaxies is incredibly high. And in some sense, we're approaching the confusion limit for galaxies. Those of you who heard Fedstock in the session this morning, she stressed just how deep these data go, and the challenge of overlap of images, and that LSST is going to be like this over 20,000 square degrees, and we're going to get some sense of the challenge that we face. So let's keep on going. I've mentioned we've had a variety of reasons for things to go slower. Poor weather, then Mauna Kilauea decided to start erupting, and now of course COVID-19, although observations have started again. But in many ways we're nearing the end. This on the left-hand side shows the survey footprint in a series of mostly equatorial fields in the I-band, and a key message here is that the seeing of these data is really exquisitely good. The median seeing in the I-band is 0.6 arc seconds, which is actually a little better than the LSST requirement. So it's again, it's worth comparing HSC and the Rubin Observatory. Ours is the Subaru telescope has an aperture of 8.2 meters. Rubin is an effective aperture of 6.5. The HSC has only a field of view of 1.7 square degrees. So the overall étendue is about 1/3 that of Rubin. And so you can very much think of this in many ways, although not in perhaps every way, as a Rubin precursor. I already mentioned the 3 layers. The deepest layer is really doing one of the things that's really going to be key for Rubin Observatory, the LSST, which is searching for transients and variability of all sorts. And again, the co-added depth is getting a little bit deeper than what Rubin should be reaching. And the data reduction challenge is very similar between the two. And indeed, the data reduction effort is between the two projects is very closely tied. They use a common code base, and the HSC data are just used extensively for testing the algorithms. So the AGN Science goals for HSC mirror many of the topics that we're all familiar with. Those people who have been involved in the LSST AGN Science collaboration are familiar with. But again, remember, HSC covers far less sky. I mentioned 1,000 square degrees, not 20,000. Doesn't go nearly as deep as LSST over most of its footprint. It has no U-band and really has only limited ability to probe variability. So I want to talk through some of the science results that have come from HSC and use this opportunity to sort of make some points about where where the Rubin Observatory, where there's lessons to be learned or scientific opportunities going forward. High redshift quasars has been a game that I've been involved in a very long time, and Yoshiki Matsuoka has been the person who's been leading this effort at Ehime University in Japan. We now have close to 100 spectroscopically confirmed quasars with redshifts above 5.7. Our highest one is just under 7.1. And what one can do with this deep imaging is really probe to quite low luminosities, absolute magnitudes of -23, or even just a little bit fainter. And it's with this kind of quality of data and depth of data, we found that the selection of high Z quasars is very efficient, in the sense that the vast majority of the things that we spectroscopically target and end up indeed being quasars. But a key lesson that's I'm going to be coming back to, is that much of the science has really followed from doing really extensive follow-up. You need the spectroscopy, first of all, both in the optical and the infrared, ALMA, X-rays, radio, and so on. And this is going to be a major theme for the Rubin Observatory as well. So, okay, let's see. Let's just continue. So it's, I don't need to tell this audience perhaps the challenge of finding rare, the extraordinarily rare high redshift quasars. But the basic technique is, as people who do the high redshift quasar game, is to look for the dropouts, the objects that only show up in the longest wavelength bands. And this is illustrated with one candidate here, invisible in G, R, and I, and showing up in the Z and the Y band. And the way that these objects are selected is to write down formal Bayesian selection probability of whether this object might be a star or a quasar, given its photometry, and therefore get a probability that the object is a quasar indeed. And so what you're doing is, in a probabilistic way, asking where stars and quasars lie, and selecting objects this way. So, and then given objects that are a high probability to be quasars, then do the spectroscopic follow-up. So on the x-axis is the probability of various candidates that come out that they are quasars, and as colored here is an indication of what the spectroscopy actually told us it was. And as you can see, there's objects with high probability of being quasars have spectroscopically been confirmed overwhelmingly to be indeed quasars. There's some galaxy contamination, and objects that this formalism says are unlikely to be quasars usually indeed spectroscopically turn out not to be quasars. So it really does work remarkably well. So one of the things that's worth mentioning, and is definitely relevant for the Rubin Observatory, is that in the wide layers, sort of the area of sky over which we've done most of our selection, there's typically 6 back-to-back exposures in each of I, Z, and Y filters. And that has been tremendously useful when comparing the photometry on each of those exposures separately. Allows one to get rid of a lot of false positives, cosmic rays, and various glitches of one sort or another. And that will, for any search for rare objects, certainly selected by photometry, that will be a key issue with the Rubin Observatory as well. So we have lots of spectra. I already noticing the time and have a lot more to talk about. So I'm actually gonna not have a chance to explain everything, but let me just show you average spectra of as it were, ordinary quasars that we found in the upper panel. The black histogram is our objects, and the various other histograms are comparison objects from other surveys. That we found this interesting category of what we call narrow line quasars. Whether that's what's really going on, we're not quite sure. Very high equivalent width, fairly strong continuum, but it's not completely obvious that these are AGN in the usual sense. And there's the average spectrum of them. And indeed, even though we also have a morphology cut, we do select against things that are obviously extended. We do have some contamination from galaxies, and there you can see the average spectrum of the galaxies that we found thus far. So, and this just shows again where these objects end up lying in color space, and again the blue points are the objects that are spectroscopically confirmed quasars. So there's all kinds of science to do with this, and I'll sort of do a whirlwind tour and probably have to skip some. One can measure the luminosity function. We're probing down to absolute magnitudes of between about -22.5. These luminosities are low enough that it's actually overlapping the luminosity function of Lyman break galaxies at the same redshift, which is to say that another way to say this is that we probably have to seriously be worrying about what the host galaxies of these objects are doing at these kinds of redshifts. Let me just skip that. One of the things that obviously comes up is when trying to understand the spectroscopic, the physical nature of these objects, we want to get spectra that go into carbon-4 and longer emission lines, which means near-infrared spectroscopy. When you're looking at objects that have AB magnitudes in the Y band of 23rd, near-infrared spectroscopy is really hard. You have to, these are each of these spectra from a paper by Masafuse Onoe et al. Each of these spectra represents many hours with GNIRS and X-Shooter on the big telescopes. An interesting result is that the black hole masses we're inferring are still remain high for these objects, and these things are not accreting at full Eddington. They're relatively low luminosity. The Eddington ratios are about 0.1 or so, which is an interesting result. We're doing ALMA follow-up. Takuma Izumi et al. has led a pair of papers exploring dynamical masses of the hosts. We've detected hosts, the C2, for example, from the hosts of a variety of these. And just to finish up on the high redshift quasar front, I just wanted to re-emphasize that point that we're really limited in practice by the by our ability to do follow-up. I mean, we could keep ALMA and a variety of 8 to 10 meter class telescopes busy quite a lot of for a very long time to follow up all of our objects, and so our conclusions are limited by not by the number of objects that we have, but the number that we have time to follow up. So I want to just say a few words about quasar host galaxies. Now I'm going to switch to lower redshifts. You know, with the excellent seeing, I mentioned the 0.6 arc seconds in the I band, the very deep imaging in the wide field, we really can, HSC can see host galaxies pretty unambiguously for essentially all the galaxies to redshift of 1. And that's, again, going about a magnitude or magnitude half less deep than LSST will do. And so, you know, here's just a gallery of a variety of objects at a redshift of a half. This is from a senior thesis by Michelle Baird, who just finished her senior thesis here at Princeton. One of the games that can be played, and this is from a paper that's just been submitted to publications of the Astronomical Society of Japan by Toru Ishino, is to do just look at the radial profiles, azimuthally averaged brightness and fit models to that. And one of the things that this game reminds us is that, you know, with the images you can do more than fit Sirsic profiles. You can see substructure, companions, spiral arms, all kinds of wonderful things. And you can see the objects in this slide have redshifts that range from 0.4 to 0.7. Another fun example, John Silverman has been leading this effort, is taking the SDSS objects, looking for SDSS known quasars, and looking at the HSC imaging and seeing if you see examples of dual quasars, 2-point sources. And a number of these objects have shown up. Spectroscopy shows that a fraction of them, not all of them, are indeed physically dual quasars. And just one more example of something fun. This was part of Ailey Sun's thesis at Princeton. By looking at multiband imaging here of obscured quasars, one often sees evidence for extended emission line regions. And the left-hand side is the RIZ composite of one particular object at redshift of 0.4, and playing the appropriate image subtraction games, you can sort of isolate the oxygen 3 emission from this object. So
About 2 minutes, Michael.
Okay, I'm going to skip this, although it's great fun. You can do galaxy merging and other such things, environments of quasars, but I want to get to sort of my themes which I want to emphasize here. So, you know, HSC is really just getting started. We've been in survey mode for oh my goodness, already 5 years, but there's, you know, we're in many ways just getting started on the kind of science that AGN science that can be done with wide field multiband imaging to the kind of depth that we're going. I have 26, 27 is even better. The synergy with other facilities is really, really important, and something I imagine that in this workshop we'll be talking about. You know, with the Rubin Observatory, it's just going to be that much more difficult. The first statement is that the sample size is going to be so much larger than that what we're talking about. We're not even up to 1,000 square degrees, and we have far more objects to follow up than we possibly can with facilities, radio, X-ray, spectroscopy, and so on. And the other thing is that, of course, Rubin will allow us to go yet fainter, which of course we will want to do, but it becomes more difficult in all kinds of ways. The follow-up gets harder when you go fainter. The flux from those host galaxies, the host galaxies of those objects will be even more of a contamination as one goes to lower luminosities, and so that will be an important thing. Just a throw out to say that there's yet more subjects that we could have talked about, and in probably the I should just mention that the HSC has already had 2 public data releases. So we have already released something like 300 square degrees to the full HSC depth in all 5 bands, and another 800 square degrees with partial coverage. And the HSC pipelines, as I said, are being developed in coordination with LSST. They continue to evolve, but the photometry really is excellent. And the biggest challenges are sky subtraction. I think I have just finished up my time, and object blending. The deblending problem is a key one. So had I more time, what I would, let me just sort of finish with this slide here, is that the prime focus spectrograph on the Subaru is sort of the next thing. And let me just very quickly say, I think I have another 2 minutes. You said I could go in there. There'll be 1 square degree field of view for this prime focus spectrograph with 2394 spectroscopic fibers, coverage from 0.38 to 1.26 microns in a single shot. And we're planning a 360-night spectroscopic survey, starting about the same time that Rubin Observatory should start its survey, with targets selected from the HSC data, and a selection of AGN will be one of a number of science goals that will happen there. So why don't I finish there and ask if there are questions.
Great, thanks a lot, Michael. So everyone, if you have some questions for Michael, please enter them in the Q&A box now. I can start off with just 1 or 2 questions while people type theirs in. To start with, you had mentioned along the way that there is no U-band. Can you remind us technically why there is no U-band? Is there something about the instrumentation?
It's the optics. It's the optics itself.
Okay.
Yeah, the coatings, both the primary mirror and in the wide field corrector, mean that the throughput with Subaru in the U-band is really quite poor. And it's not, one could put a U filter in and very, very slowly gather U-band data. It turns out to be considerably faster, for example, to go to CFHT, which is a mere 3.6, 3.8 meter telescope, which has much better throughput in the U-band.
Okay.
So we have done, there is an effort in the HSC deep fields, those 28 square degrees, to get data to about U of 27 over most of that area, and most of those data are in hand, and that's been led by Marcin Sawicki.
Okay.
Yeah.
A couple more questions now. So a couple have come in. So Gordon Richards is asking if you could remind us, perhaps take us through in a little more detail, what HSC data are public. I think you mentioned it on a previous slide, but just a little bit more of a show and tell on that can be helpful.
Yeah, I don't have slides, and I'm not sure I have quite all of it in my head. So what are available are the images themselves, the raw data, the processed data, the full catalogs as processed. So each of the two data releases, as the pipelines have evolved, the data releases the first data release uses a different version of the pipeline than the second one, but they're fully searchable online catalogs and a quite sophisticated interface to the images themselves, a way to sort of view the data as well. So yeah. So
go ahead.
I mean, the data. One of the things that has been a matter of some discussion is whether we can make the user interface for the HSC data look like what LSST will eventually, Rubin Observatory will eventually make available. They're just that has not happened, in part because at the moment yet Japan is not yet part of the Rubin Observatory consortium, although there's active work to do that. But there's an increasing convergence of different approaches to databases and user interfaces to try to make those make the HSC experience of working with the interfacing with the HSC data look like what it will look like for LSST.
And aside from the general 300 square degrees that have been publicly released, like the AGN Science collaboration has a lot of interest right now in the XMM-LSS field, because we may use that as a data challenge field. I know some of that has been released. Do you recall some of the details there?
I cannot quote off the top of my head just how much is there. I should know that off the top of my head. But yes, that is one of the key fields, and of course that's also there's a set. Had I more time, there's a whole other sort of sub interaction between the XMM team and the HSC team, and doing a variety of both AGN and cluster science, and of course looking into the future for eRosita and so on.
Okay. A couple more questions have come in. Here's one from Paula Sanchez. She asked, can you detect some variability from the high redshift quasars using the Hyper Suprime-Cam? I guess in the fields where you have multi-epoch. Yeah.
So the quick answer is, at least at the high redshift end, essentially all those quasars are selected from what we call the wide layer, where I mentioned in passing that we get 6 exposures of 200 seconds each in I, Z, and Y, and 4 exposures in G and R. We typically take those 6 or 4 exposures more or less back to back. That is, we do not have a synoptic piece of that part of the program, if that makes sense. Which means, unfortunately, for the very rare objects that are spread over very large areas, we don't have time variability on anything like an interesting timescale. In the HSC deep fields, which are 28 square degrees, and the ultra deep field, which is a subset of that, which is 3.5 square degrees, there is variability information, but those are such small areas that there's really nothing to say on the high redshift end. People have not done this. There's much scientific opportunity there, I think, to go and look at the AGN variability questions in those data. There has been some work looking for TDEs in those data, and I think there's a handful of objects published. But this is the kind of area where you realize that the Rubin Observatory is just going to blow HSC out of the water. This is something that HSC really can only start to scratch the surface of, and Rubin Observatory is much more powerful.
Okay. Here, and then another question from Swayam Panda asks, can you talk more about how the host galaxy contribution and the AGN are decoupled in the nearby quasars observed with the Hyper Suprime-Cam, and how will this be important in terms of LSST?
Well, that's a good question. So let's go back to this. So there are various techniques to fit an image like what one sees here with, as it were, a point source plus as it were a Sursec profile. Or if you're looking at the middle of these objects, you probably want to fit definitely need to fit multiple components. So there, we've started some of this work. I showed this figure earlier. What's shown on the right-hand side is the radial profile of this particular object. That is, this is a central PSF plus a SERSIC, and that's the model that's shown here. The blue, notice the y-axis on this graph is logarithmic. The blue dotted line is the model of the PSF, and the SERSIC profile convolved with the PSF is the is that pink dashed line, and the sum of the two is the green, and it fits pretty well. And given that model, you can subtract off the central PSF, and you have a model for the host galaxy, or the residuals are sort of, by definition, your best guess as to what the host galaxy is. Is that good enough? Perhaps in a radial profile way, it looks pretty good. One of the things that comes out is in fits like that is objects in which that fit has large chi-squared, meaning that the fit is not very good. That's often a sign that there's substructure or companions or spiral arms or all kinds of things. And so there's a great deal of scientific opportunity there to go dig into this. And I think this is, I think we're only starting to think about what the right way to do this is with this sort of quality of data. And it's going to be a key question for the Rubin Observatory. So
Okay.
I'm hoping it's something we can discuss as we go forward.
And perhaps just one more question as you are unloading your slides. If you can stop screen sharing, Michael, and so Qingling can start sharing hers. So the final question: have you seen any impact in your data? I guess your more recent data from the Starlink satellites.
A quick answer is no. No,
Okay.
but we've basically, as Starlink was getting bad, we were shut down by COVID-19. So
okay,
so,
right.
Okay. Well, thanks everybody, and
thanks a lot.
I'll say goodbye. Okay. Bye-bye.
Oh, okay, so the next speaker will be Qingling Ni, who will be telling us about the XMM-SERVS survey of the LSST deep drilling fields.
Hello. Hope everybody can hear me well. I'm a graduate student at Penn State working with Neil, and I'm very glad to be here and present the XM-SERVS survey of the LSST deep drilling fields, which includes a lot of efforts of the whole XM-SERVS team. So basically, my talk will consist of 3 parts. In the first part, I will talk about how would X-ray coverage in the LSST deep drilling fields help. In other words, I would like to introduce why would you care about the X-ray coverage in LSST deep drilling fields. And in the second part, I will talk about the design of the XM-SERVS survey, which is providing good X-ray coverage to the LSST deep drilling fields. And in the third part, I'm going to introduce the most up-to-date XM-SERVS results in the 3 of the LSST deep drilling fields: XMM-LSS, WCDFS, and ELIAS-S1. So before I go into all the details, I would like to introduce what are the LSST deep drilling fields. Although I know that some of my audience will know for that pretty well, but just introduce that again for a broader audience. So there are 4 selected LSST deep drilling fields: Cosmos, XMMS, Extended Chandra Deep Field South, and ELIAS-S1, represented by these red circles in this map. And there might be more deep drilling fields, but it's still under discussion. So for each of these deep drilling fields, they're likely to get thousands of visits in UGRIZY band separated over a 10-year period. And for the GRIZY band, it is very likely that each DDF will be observed every 2 to 3 nights when visible, and the cadence in the U band is relatively unclear. So with this cadence strategy, we can get approximately 26.5 to 28 Mach in the UGRZY bands. The 28 corresponds to GRI band, and the 26.5 corresponds to Y band, and U band and Z band is somewhat in between. These numbers could vary by 1 Mach between different OPSIM strategy and different fields. So how would X-ray coverage in these LSST deep drilling fields help LSST AGN Science? As we heard in the talk this morning, the most important thing is that it could help AGN selection in LSST. AGNs identified in the X-ray could serve as a ground truth sample of AGNs in deep drilling fields to calibrate the LSST selection algorithm via color, variety, etc. And after calibrated in the deep drilling fields, we could further apply it to the main survey. And in general, X-ray emission serves as a reliable way of selecting AGNs, as it's nearly universal among luminous AGNs, and it could penetrate large column density except for really Compton thick objects, and it has low dilution by host galaxy starlight. It has also been argued that the X-ray selected AGNs are less biased in the distribution of Eddington ratio, specific accretion rate, though I need to admit here that different AGN selection methods in different wavelength bands all has its own advantages. But in general, X-ray is a very reliable way for selecting AGNs. And also with the LSST selected AGNs, X-ray coverage could help to characterize the multi-wavelength properties of them. As the optical to UV emission is dominated by the disk, and the corona dominates in the X-ray, linking the X-ray to the optical could probe the link between the disk properties and corona properties. And also, if we only study a purely optical selected AGN sample, we can easily get biased towards an unobscured AGN sample. And when we include AGN selected in the other wavelength bands, such as X-ray, we will include more obscured AGNs and low luminosity AGNs. Here I have a nice plot showing how the AGN plus host galaxies SED change as a function of AGN dominance and obscuration. And we can see that even the AGNs is not that dominant, and the obscuration level is pretty high. We still observe point-like emission in the X-ray. Last but not least, X-ray coverage could help us disentangle the AGN contribution in the SED and measuring the host galaxy properties utilizing the empirical correlation between the intrinsic optical luminosity and X-ray luminosities of AGN. Here is an example from Yang et al. 2020. He performs SED fit-in to a Cosmos Type 2 AGN. In the left panel, he only uses the UV to infrared data, and he got a solution with an AGN of a small intrinsic optical luminosity, which is unlikely to be true given the actual luminosity of this AGN. So if we incorporate the X-ray data into this fit-in and rule out the unlikely solutions by applying this empirical correlation between intrinsic optical luminosity and X-ray luminosity, it will help us to break the model degeneracy somehow when performing the Galaxy plus AGN SED templates fit-in. And this is the solution he got after applying the X-ray constraints. So with all the advantages X-ray coverage could bring to the LSST AGN Science in mind, the XMM-SERVS survey is providing good X-ray coverage to 3 out of 4 LSST deep drilling fields. And the one not included is Cosmos. And the reason for not including it is that Cosmos has already got a good X-ray coverage inside the LSST field of view, represented by this large black circle. And there are already Chandra data and deep Chandra and XM Newton data inside this 2 degrees square region encoded by this blue square. So we mainly focus on the 3 remaining deep drilling fields. As for the XMM LSS field, there are already plenty of X-ray surveys in this field before XM-SERVS, and the largest one is XMM-XXL. It provides 10 kiloseconds XM Newton depth to a very large area. And this is a nice survey for studying X-ray clusters, large scale structures. However, if our main science goal is AGN study, we certainly want to go deeper. With the 50 kiloseconds XM Newton depth, we could probe 10 times below the mean luminosity of the X-ray luminosity function, and we can include 70% of the cosmic accretion power with our survey. And the luminosity distribution of the probe AGN with a 50 kiloseconds XM Newton depth is shown here as a blue histogram in comparison with the probe AGN luminosity with 10 kiloseconds XM Newton depth represented by this red histogram. We can see that increasing the depth, we are going to probe more moderate luminosity AGNs. As for the remaining 2 fields, WCDFS and ELISAS-1, Here, WCDS is similar. It's just the same as extended transit field cells in the deep drilling field definition. But in our XM-SERVS survey, we call it WCDF. It's just because there are already some extended transit deep field cells, which corresponds to a small region. So compared with the rich multi-wavelength data in other bands, such as in the background, you can see this gray field region, which has data from the Spectre Deep Drill survey. There are also good near-infrared data from the Vista video surveys. There are also a lot of optical coverage in these fields already. So compared with this rich multi-wavelength coverage, the X-ray coverage is incredibly small inside the 10 degree squared LSST field of view. For WCDFS, there are only transient coverage in a 0.3 degree square region. And for Elias S1, there are only XM Newton coverage in a 0.6 degree squared region. So with all these in mind, we designed the XM-SERVS survey, which observed the 12 degree squared Spectre extragalactic representative volume survey. This is a 12 degree square region represented by this yellow squares here inside of the 3 LSST deep drilling fields. So aligning the X-ray footprints with this SERVS area is not only because of some it's economical to observe some smaller region. It's also because the SERVS area has the best multi-wavelength coverage inside the LSST footprint at that time. And the details of the multi-wavelength coverage from radio to UV could see in Chen et al. And here is the archival link of it. You can refer to this paper if you have interest. So it has good near-infrared coverage. There are also HFC in the optical already. There are also incoming radio data from MIDI, incoming spectroscopy from MOOMS and PFS. There might also be some millimeter observations from ELMA and TORTEC in the futures, which all has great legacy values. So now I'm going to provide you with the results of the XM-SERVS surveys. Our first field, XMM-LSS, has already been completed and published as Chen et al. 2018. Our XMM-SERVS survey provides 1.1 million seconds additional good XM Newton exposure to this area represented by the blue black square. And in this black square, we reach a 50 kiloseconds depth for most of the region. I also roughly plot the LSST footprint as this blue shaded circle, so you can see the relative alignment of the XM-SERVS footprint with the LSST deep drilling field. By design, we reach a very uniform sensitivity through the probe region, and this sensitivity is certainly improved compared with archival data only as a dash curve here, and our current sensitivity curve is the solid line. And I also listed the sensitivity number if you have interest for future reference here. So with this sensitivity, we detect more than 2,000 X-ray sources. And I won't spend time here to introduce how we deal with the source detection process in XMM-SERVS. Instead, I would like to mainly focus on the multi-wavelength counterpart matching process, as finally we would like to match these X-ray sources with LSST sources. So among all the X-ray detected sources, 93% of them are considered to have reliable counterparts in the optical and or near infrared from Spectre SERVS, which covers 3.6 micron, 4.5 micron, and video, which is Vista survey in ZY, JHKS bands, and also CF, HTLS, and HST SSP, which are 2 optical surveys. And they are shown by the blue dots in this figure, and the red dots correspond to those that match with reliable counterparts. Due to the high density of the optical and near-infrared catalogs and the positional uncertainty of XM Newton, sometimes multiple solutions could exist when we match multi-wavelength counterparts. And we could, of course, select the one with the largest likelihood based on the distance and some defined priors such as magnitudes or colors, but we are still not 100% sure if the matched counterparts are the true counterparts, as likelihood is just likelihood. So in order to assess that, we perform Monte Carlo simulation to assess the force matching rate when matching X-ray catalog to each of the optical or near-infrared catalogs. And the formula is listed here, and you can refer to the paper for more details if you have interest. So the result is that we found that the SERVS catalog has the smallest force matching rate among all the catalogs, and the optical catalogs has the relatively high force matching rate. So when matching X-ray sources to multi-wavelength counterparts, we select a primary counterpart in following the priority order, SERVS, video, and then optical catalogs. And after selecting these primary counterparts, we adopt a constant searching radius of 1 arcsecond to associate this primary counterpart with objects in other optical and near-infrared catalogs, as optical and near-infrared catalogs have smaller positional uncertainty. And most of our X-ray sources are matched to SERVS as a primary counterpart. One important goal of identifying the multi-wavelength counterpart is to obtain the redshift of these X-ray sources. Redshift measurements are important for characterizing AGNs, as we finally want to convert the measured flux luminosity and convert the observed frame properties to rest frame properties. Around more than 1,700 X-ray sources have SPEC-Z, and with the force photometry from U-band to 5.5 to 4.5 microns of these X-ray sources, photometric redshift could be derived to provide additional sources of redshift. And of the more than 3,000 non-broadline X-ray sources with force photometry, more than 2,000 of them have high quality photo Z. So in total, 70% of X-ray sources in our prime region has SPEC-Z or high quality SPEC-Z. Here I plotted here are figures from Chen et al. 2018 showing the distributions of SPEC-Z and photo Z and how the number of SPEC-Z or photo Z vary as a function of HSC I-band magnitudes. So if we compare the SPEC-Z and photo Zs, we could find that for non-broadline AGN sources, the photo Z measurements are generally very reliable. With all this information, around 97% of the X-ray sources are classified as AGNs where broadlines or very luminous rest frame X-ray luminosity, or large X-ray to optical or X-ray to near infrared flux ratios, or by the IRAC color selection if it is detected in 4 IRAC bands, which is available for 1,700 X-ray sources. Well, by using these X-ray sources, we also perform comparison of X-ray versus mid-infrared selections. And there we tested different mid-infrared AGN selection from Lacey wedge, Stern wedge, and also Donley's criteria. And Lacey's wedge is the most complete one, and it detects 1,300 around AGNs among these 1,700 X-ray sources. And we can see that it works fairly well for luminous AGNs represented by these red triangles. However, X-ray selections could minimize interlopers and find moderate luminosity system as there are more than 200 objects not included in the Lacey wedge are identified as AGNs via method 2 or method 3. Here I'm going to present the results in our second field, WCDFS. Currently, we have finished observing all the designed pointings. However, as our observing strategy is that we hold 30% of the time first in order to reobserve pointing that was significantly affected by the XMM background flaring in the first round. So some reobservations are still needed this year to reobserve these regions. Currently, we reached the 50 kilosecond step for 70% of the survey region. And here I show the X-ray image of the current all the pointings accumulated together. We can see it's much wider than the original Chandra coverage, either in Chandra diffuse cells or extended Chandra diffuse cells. With the current observations, we already detect 3,600 active sources in this field, and almost all of them are new sources. Here I plot the source distribution and flux distribution here if you have interest. So, and 98% of the active sources have multi-wavelength counterparts from Spectrograph, Vista Video, HSC survey, and the VST voice survey in the optical, represented by these color borders in this figure. I also show the LSST deep drilling fields in the blue shaded region in the background. They align very well with the XM Newton observations represented by these black circles. And up to now, 700 of the active sources already have high quality SPEC-Zs, and photometric redshift has been computed by Guangyang utilizing the force photometry catalog prepared by Christina Nyland, which combines data from U-band from voice to 4.5 micron in a splitter. And the general performance for the general galaxy population is good, and for non-broadline AGNs in the X-rays, the current photo-Z measurements also appear reliable. Our third field, LSS1, has been observed in parallel with WCDFS, although it's a little bit slower. We have now finished 19 out of 25 appointees, and 2 of them just arrived last week. And the whole observations will finish by 2021. And we so far detect around 1,600 active sources in the field. We have also computed the first version of photo-Zs in this field, but we are waiting for better multi-wavelength counterpart, better multi-wavelength data being assembled. Here is, as required, I present the opsin matrix. I'm interested, this talk mainly focused on the X-ray coverage of these deep drilling fields. So my desired opsin matrix is just evaluate whether different U-band depths in the deep drilling field could influence the characterizations of, for example, photometric redshift of AGNs in the deep drilling fields. As we know that only 5 filters could be in the filter wheel at the same time. So currently the U-band depth in most of the opsin shown is shallower than other bands. So it is good to understand how various U-band depths will influence the AGN characterization. And I will leave all the detail for further discussions in Wednesday. Thanks.
Great, thank you. So I think we already have one question, and if people have questions, please put them in the Q&A box now. So here we have a question from Il-Sang Yoon regarding, do we have any significant level of contamination from X-ray binaries?
There are always contaminations from X-ray binary, but you need to first assess it in a luminosity levels, as X-ray binaries really exist 10 to the 42 erg per second in the X-ray luminosity. So for example, when you got a really luminous X-ray sources, it's very unlikely that it's a X-ray binary. And in our XM-SERVS, I will refer back. So here, can you see the slide here?
Yes.
So this is LX distribution. You can see all we detect are moderate to high luminosity AGN. So even if there are contaminations from X-ray binaries, it's very small. It can be generally neglected. And if you want to characterize that, you are certainly welcome, but it's kind of negligible.
We have a couple more. We have another question that's come in. It asks, It's from Zuri Zhao, asks, would new star deep observations help, since we already have many XMM and Chandra soft X-ray observations in these fields?
Well, will new star help LSST AGN Science? Is that your question?
Yeah. Would it be worth getting new star coverage over these same fields?
Yes, new star is certainly good at characterizing the Compton thick AGNs compared with Chandra and XM-Mutant. But one thing you need to notice is that new star's positional uncertainty is not that good. So if you want to relate the new stars AGNs detected in new stars to directly help LSST AGNs, there are a lot of sophisticated methods you need to done in the multi-wavelength counterpart matching, and it is really expensive to carry out some new star surveys comparing with XM-Mutant. XM-Mutant has a large collecting ability, and if you want to carry such a survey at similar level with new star, I'm not sure how difficult it will be, but I think new star follow-up is certainly good.
Yeah. I've played with I've toyed around with the new star proposal of that type, and it's a very challenging endeavor in terms of cost, and then in terms of finding a truly compelling killer app that can justify that level of cost. But it's something that certainly is on our mind. Here's another question from Swayam Panda, asks, for the broadband photometric fitting that you're doing, which I presume is using XGAL, what are the features for the AGN model used, especially how is the X-ray part modeled? And this is referring to your slide near the introduction where you showed the two different cases with and without the X-ray data.
Oh, why I can't see the questions directly. Never mind, I will.
I'm happy to repeat it if that's helpful. It's this one, yeah.
Okay,
so the question is, yeah, what are the features for the AGN model used? So what is the AGN model being used here? And then how is that allowing you to separate out the two options?
Oh, so this you can refer to this paper for more detail. If you have interest, I can give you the link here. So basically, it just incorporates the AGN's intrinsic distribution, disk luminosity, disk SED with some torus obscuration, using a clumpy torus model skirter, so that you could model both type 1 AGNs and both type 2 AGNs. So when I talk about intrinsic optical luminosity, we have already accounted for this obscuration from the torus. And let me find this paper, and maybe I could leave it in the chat window. And the AGNs follow some empirical correlations from X-ray luminosity and optical luminosities. It's empirical correlations well studied for more than 10 years. I can also show you these papers if you have interest. And so if the fitted AGN from a pure Galaxy plus AGN templates, if you only include UV to infrared data, it may give you a solution which only accounts for which give you a unreasonable small intrinsic optical luminosity when it is actually luminous in the X-ray. However, if you incorporate the X-ray data in the fitting, and you find that it should be that unluminous in optical, then you could rule out those which is just results of model degeneracy between AGN and Galaxy templates, and rule out those unlikely solutions which might help break out the degeneracy somehow. So I will try to give you the paper.
Right. Thanks. Okay, and so with that, I think we need to move on to the next talk. And so, Qingling, if you could maybe just email Swayam, you can provide the link to, that's great.
Yes.
Okay, so if you could stop sharing the screen, then Mauricio, you can take over the screen sharing and we'll get you set up.
Okay, you hear me?
Yes, we can hear you just fine. Yes. And so we are now going to hear from Maurizio Paolillo, who is going to tell us about AGN detection and characterization through optical variability, and specifically the lessons learned from the VST supernova surveys that he's been working on.
Okay. Good evening. Thanks for staying here, especially for the European friends for whom it's late. So I'm going to talk about the work done in the last few years with this small telescope here, which is the VST on Paranal. And of course, you already heard from other people all the different selection methods that can be used to select quasars and AGN, spectroscopy, SED fitting, X-ray, optical, UV color, radio emission, and so on. And so now we're trying to put variability into play, which has been done in the past, but it was hard to obtain for very large sample and large area until recently. And I mean Hyper Suprime-Cam and other facilities, including VST, as I will be talking. But of course, LSST and the Rubin telescope will make a huge difference. So when we started this a few years back, there weren't so many studies going very deep. And I'm just showing a few highlights just to show that we were trying to push the boundaries, what could be done with variability. So for instance, in this work by Treves et al. In 2008, looking at the Chandra Deep Field South area, they were able to retrieve by variability AGN, and 60% of these were the variable source were able to be confirmed over a 2-year baseline. Other study tried to go use a higher resolution. For instance, this is the work by Sargedini in 2000, in which using in the Hubble Deep Field North, they were looking at variability for AGN and trying to discover AGN based on the difference between two epochs. And they were finding, you know, the field is small, so a minority of AGN. The interesting thing is that here they could compare with X-rays over the field, and basically 10% of only of these were confirmed by X-ray emission, although they were going pretty deep. And another case is this Villefort 2010, in which they cover the goods field, and in this case they again make use of the HST resolution, and they can find a few percent variable sources. And the interesting thing here is that they were going pretty deep, and with the HST resolution here, you're really digging out the population of low luminosity AGN, which are hard to retrieve from the ground. And in fact, when we compare with their results, we find that their objects are typical low luminosity AGN hidden inside the galaxies. So our work was started using piggybacking on supernova surveys that were designed and that were organized with the VST telescope, which of course it's much smaller than LSST, even Hyper Suprime-Cam is just a 2.5 meter telescope with a 1 degree field of view. At the time was competitive, but still it could allow to achieve better results than what had been done that far. And so we basically used the data from the SUDARE, the supernova survey, which was taking R-band exposure every 3 days and G&I exposures every 10 days. And this was joined by the voice survey, which was getting additional data, especially in the U-band on some of these fields. So it was, in the end, it was arranged to have a synergy and to work together for common goals. And in particular, I will be talking about the Cosmos field, in which the VST observed 1 square degree over, by now, 3-year observing baseline with more than 60 epoch, and the Chandra Deep Field South, in which we cover a larger area of 4 square degree, but each field was observed only for 1 season, basically. Except, no, well, the first one for 1, and some of the others for a slightly longer, with a slightly longer baseline. So just to show the field, you've already seen the coverage. So these are the CDFS and the LICE fields, which have been covered by these cyan squares, which are the VST field of view. Here in the center, you see the extended Chandra Deep Field South, the the original one. This is the ELICE. In the ELICE, however, there is no variability. We're trying to get it now. And then there is the Cosmos area, which is only 1 square degree. It's the red area shown here. I will explain why there are all these gaps. And these are the X-ray catalogs. Actually, the Chandra catalog now it's larger. This is from the old 2012 catalogs. But anyway, here the VST could observe the whole, almost the whole field in one shot. So the inconvenient truth, when I think that's something that we have to think about in thinking about LSST operation, when we started doing this, we had, of course, all sorts of problem, aesthetic artifact, defects, tracks, even this is one star from the laser from one of the nearby telescope in the sky. And so if you want to get variability data and good photometry in this area, you have to think about what approach to use. Our solution was just to get mask to exclude all the region that had problems. Of course, this has an impact, for instance, for the LSST, because we have to decide if we need, for instance, to have specific diagnostic FLED, image cutouts, in what way we will be able to assess the reliability of our variability in such a huge data set that will not be able to be explored by eye individually. So after correcting all of this, of course, you have to take into account the 0-point offset that come with problem in calibration, which is a few tenths of magnitude. And what we did was a very basic approach, nothing compared with what Gordon was talking about earlier. This is just looking at the RMS variability, so no sophisticated fitting of the light curve whatsoever. And we're doing just aperture photometry here, which of course can be improved and will be different with image difference analysis for LSST. And of course, once you correct for aperture photometry, you get a much better handling of the uncertainties. And so the result that we got, for instance, here's a snapshot of the 4 CDFS fields in which you have the RMS variability on one hand, and then the gray, or in this case, the cyan objects are the ones that are basically non-variable, the most of the object. And this is the threshold that we use. We were originally using a conservative 99% threshold, and then we moved to a more relaxed 95% threshold to identify all the objects that vary above average. So the goal here was to try to understand what we could retrieve based on just variability without any other color selection or any other additional indicator, additional diagnostic. So this is an example of the Cosmos, one of the light curve in the Cosmos field, and the CDFS. In the CDFS, we have 27 epochs over 5 months, and this is a typical light curve of a supernova, where the error bars here are computed looking at the scattering in the source. So it's not hypothetical; it's measured on the images themselves and including all calibration uncertainties, and clearly AGN stand out. But you are contaminated by AGN when you look at variability. Of course, when you go to much longer baselines, like the Cosmos, which spans 3 years now, it's the contamination from supernova becomes much smaller because the supernova disappears, and while AGN have often this huge variation because of the red noise variability. So how good are these detection compared to other diagnostics? For instance, we heard from Qingling how effective and important the X-ray detections are. So we were able in the Cosmos to look at the X-ray sources, and these triangles here show the X-ray sources in the field. So you can see that the minority of these are above the threshold that we set to detect variability. And so in the first season, we could only detect something about 15% of the X-ray selected AGN. However, as expected in part, and we predicted it based on structure functions, once you go to 3 years, this fraction increases significantly. And you can see that you go to a much larger completeness with respect to X-ray sample, the threshold becomes lower, and then you're starting to get about 40% of the X-ray sources. So at this point, of course, one obvious metric for AGN selection is the total baseline, and of course, even the cadence. And so we would suggest that you need at least 3 years of data to start to be somewhat comparable to X-ray observation, somewhat. And this is in part already fulfilled by the current plan. But what could be important, for instance, is to have precursor surveys, take advantage of data from VST, Hyper Suprime-Cam, and other surveys to extend the baseline so that you are effective in detecting AGN even in the beginning of the survey without having to wait 3 years to dig out large samples of objects where you don't have the X-ray data. So once you look at the variable source, you could see that basically 85% of the variability selected AGN are confirmed by X-ray properties. And which means that we're very clean in selecting very pure samples in which the contamination is relatively low, and all of them lie in the diagnostic, in the strip of AGN strip in optical to X-ray ratio. So optical colors and near infrared are useful in particular to disentangling these variable objects, which are the large circles, and from, for instance, the stars, which lie here in the sequence. So you can remove some of them by optical colors. But of course, there is some cross-contamination here. And from LSST alone, we will not have infrared bands like the K-band here. So of course, additional synergies with other facilities are extremely important. And if you look at the infrared diagnostic to see how we compare with infrared data, you can see that the variability selected object, both in the cosmos and CDFS, align very well along the power law region, even within the lazy region, they clearly define the AGN stripe where the power law spectrum lies. And they can even push to the region where there is some contamination, so there is ambiguity if an object is a galaxy or an AGN, because if you add variability on top of that, the chance of having those together is lower, and you can push the selection in the regime of low luminosity AGN. So the main result of this work that has been done in the last few years is that in terms of contamination, you will get a 3% contamination by supernovae and a 10% contamination by stars in these fields, of course, which are exagalactic fields, without doing any special analysis. But in particular, you will get extremely pure samples, more than 80% purity in whatever field we looked at of AGN. So the contamination is relatively small and can be definitely improved, including colors and including a better assessment of the properties of the variability of the light curve, like doing assessing the presence of periodicities and so on. In terms of completeness, we're not doing so well because you are between 40 and 60% complete with respect to X-ray or spectroscopically selected samples. So we're still missing more than half of the sources. And there is a strong dependence in part of magnitude and on the type of AGN. Our survey basically, in these cases, you mainly retrieve type 1 AGN, and you're much more limited in type 2, which are a fraction about 20%, between 10 and 20% of type 2s. And with respect to infrared selected, you have about 50%, and then again it depends how obscure the object is, because you're missing the AGN emission if it's too obscure in the optical. So where can we improve this? Of course, there is a lot of space for improvement. For instance, one thing is we try to look if you fold in the variability in all bands, because I forgot to tell you, so far this was based only on the R-band light curve, which are the better sampled ones. So once you go to you fold in the other light curves in the other band and you look for correlated variability, then you get this. So this is the R-band result, and you can see a lot of spurious source. This is the number more or less expected by just setting a 5% threshold. And then when you include the others, you will get this one, and you clean the sample very well. And so basically you're excluding most of the contaminants here, more than the AGN. And of course, then the other step to do is to use image different analysis. We're looking into that in VST data as well, like the supernova people usually does, and which can help push down to the fainter AGN. In this sense, for instance, another metric that we may want to look at is the interband gap lag. So we want to be sure that different bands are observed close to each other, so that we can use correlated variability, not only to do science, but also to improve our chance of detection and identify AGN with respect to other sources. And also this is partly is already fulfilled, but we are planning to look at the OPSIM and see if there are peculiar choices that make harder to detect AGN and to clean the samples with long distance between two different bands. So in physical terms, some result that you can get, for instance, this is the structure function that you get from this AGN, and you get the result that you expect. The non-variable source are here as a function of the lag, and the structure function of AGN goes up as you expect from red noise, in very nice agreement with the literature. And what you want to be able to look at are, for instance, correlation with other with physical quantities. For instance, we have a tentative result in which we identified that there is a difference at long time scale of the structure function with the accretion rate of the black hole. Much less evident is the one with the mass, as is not conclusively proven. So with LSST, the sample will become large enough. This is just the cosmos field 1 degree, that this sample will allow to greatly expand our ability to constrain these differences. Now, what about the future? So the VST has targeted at least 3 already of the deep drilling fields that Qingling was talking about earlier. And so we have some light curve for these, although of course the region cover is a smaller part of the entire area that we will cover by LSST. So we were thinking as the Italian community to propose in-kind contribution to add additional observation and extend the baseline for this field. There are other plans with other facilities, and so we're trying to coordinate within the AGN Science collaboration, but this is something that we may want to consider, because if it's considered useful, a support from the community will help to push this in the Italian community, because we will be able to access VST for its entirety in starting from 2022. So all the time will become Italian, and so we made a plan. We try to assess what we need to do follow-up observation. And for instance, if we would sample 3 deep drilling fields in their entirety with VST, it will take something like 13% of the VST time allocated to this project, with depths that are comparable to the one expected for a single epoch from LSST. Of course, LSST is the Rubin telescope is much bigger, and so we're talking here of 30-second exposure. VST has to take half an hour, so it's not time effective, but it will complement what will come later. So at this point I would conclude saying that the point that I wanted to make here is that variability is a very effective tool to identify prevalently an obscure AGN, and that yields very pure sample. We are still behind in completeness. So the extension of the baseline to 10 years will help, will definitely help. And then we have to push also using, improving on the image difference analysis and try to dig out the type 2 and the low luminosity AGN. And I think tomorrow Demetra will talk about some improvement that can be done with respect to what we've done in the past, which was a very simple approach, just looking at the RMS variability. And we have some tentative scientific results which are limited by the size of the sample. So I would try to improve on difference imaging, to look at selection based on variability plus color, plus other priors, as Gordon was saying. Demetra is trying to do some of that, at least on the VST data, and extend the baseline on the longest possible time scale. So these profits of in-kind contribution and the proposal from the science collaborations. And then, of course, as Neil and Qingling were stressing, build training sample, because these X-ray infrared sample are only available on limited areas of the sky. So these are the one on which we will base then the selection of the rest of the survey. And I will stop here and wait for questions. Thanks
a lot, Maurizio. So we do have a number of questions that have come in. I'll just go through them in order. The first one asks, so what model are you using for your study of AGN variability? This is from David Westman, who says that he has done some work using the damped random walk model and finds that to be very useful.
Yes, no, we were not doing any work, any modeling. So this was just empirical. We're looking at the RMS variability, and then we have the reference sample that is everything else that is non-variable in the survey. And so this is totally empirical based on the data. Then of course you can fold in, for instance, a model of damped random walk and then try to push the limits of your detection based on your model prediction. We wanted to be completely model-free and just see what came out of the data.
Okay. Here's some more questions. Another one asks, how much does the measurement uncertainties in your data contribute to the RMS variations?
How much sorry, because I missed
how much does the measurement uncertainty contribute to the RMS variations?
I had this. So if you look at the slides, let me see if I can show that again. So you can see here, for instance, let me dig this out. Okay, for instance, in Cosmos, when you look here, you can see that depending on the magnitude, your uncertainty is 0.02, 0.03 magnitude. So this is a few hundreds of a magnitude. And of course, it increases when you go to fainter magnitudes. So of course, if you can improve on that, and LSST will do better, you can get a number of sources out. But I want to stress that AGN variability is a stochastic process. So you may not see the variability in the moment you're looking at. So you need also adequate baseline and a sampling cadence which will allow you to dig out this variability, because these objects are variable. And in fact, when you look at the average variability of the X-ray source that fall below threshold, it is higher than the rest of the source. So they are varying, but not enough to be detected. So you need to, to implement both baseline and cadence.
Okay. Here are some more questions. Here's one from Sebastian Honig, asks, are the light curves or positions of the AGNs you identified in the Chandra Deep Field South Field available? The DeCicco papers only seem to have positions for the Cosmos AGNs.
Yes, they are available. We have them. So we have to maybe distribute it. They're not being published as them, but we're open to collaboration. Whoever wants them, we can discuss and share them.
But the AGN positions at least are published, right?
Yes, I was thinking about the light curve. The position are published and the objects are published, and we usually publish also a probability of that object to be variable or not. So you can set your own threshold depending on how pure and complete the sample you want to be.
Right. Good. And perhaps you could give Sebastian the relevant references. I think that's what he's asking
yes,
about.
I will put it in the later.
Okay, great. Okay, yes. Yes, Sebastian, those are published. And it's been answered now already. It's in the Poulain et al. 2020 paper. Yes.
Yes.
Okay, good. Here's a question from Paula Sanchez. Asks, could you provide some more comments regarding the selection of low luminosity AGN specifically?
Yeah, so basically when we look at what we were able to extract with this very simple approach, most of our objects are quasar-like in the sense that they are dominating the host galaxy. They're not necessarily the luminosity of quasars, but they're sources dominated by the central nuclear source. And so the point now is to try to push this deeper. I think that doing image difference analysis will do much better than what we've done just doing aperture extraction. When we looked at the previous HST data and we compared the samples, what we found that they always found low luminosity AGN, and that's because, of course, with their improved resolution, they can remove the host galaxy noise much better than we can do. So I think there is only so much that can be done. There will be some limit due to the seeing that the survey will provide, and that will be our main limitation. Okay.
And then I think one final question here, and this is perhaps an adaptation of the one that Ilsang Yoon asked. Ilsang asked about color variability. So when you have LSST data, clearly your data that you talked about today were mainly just R band, so you didn't have color information. But when you have, say, LSST and you have color information, can you see about useful ways to utilize color variability to aid further with the selection? Or how much do you think having multiple bands will help generally?
That's what I covered in one of the slides. So I think that multiple band are very important, because clearly once you have multiple band, the selection, the variability is correlated, that will remove a large fraction of spurious source, so we can push. So your combined probability for an AGN will be much better than any spurious source. And then, of course, if you include some modeling of what you expect the variability to be, you can even push further. But that's, it's model dependent, so it has to be simulated. So I think that having multiple bands, I would say at least 3 with comparable depth, would be extremely useful, apart from, of course, the science that you can do for that, but even for the selection itself.
Okay. Yeah. And the standard lore, I guess, is that AGNs tend to become bluer when they get brighter.
Yes.
And is that the type of modeling you're referring to there?
Yeah, I wasn't especially thinking about that. Of course, in the case of VST, the bluer bands were less efficient, and they were sampling with the lower cadence. So we didn't use those primarily. But for LSST, I think that will definitely improve. So it could even be that the bluer band are the most effective to dig out, because they will have, if they have similar cadence to the other band.
Okay, great. So I think that's all the questions that we have. And so given the time as well, I think this is a good time to stop the session. I will just end by mentioning that this is just session number 2 of 6 of these sessions that will make up the meeting in a meeting. The next session is going to be tomorrow morning, starting at 11 a.m. Eastern time. This is session 202. And there will be 3 talks there. I think first Dimitra Chico will pick up on this type of work and discuss variable AGN selection, specifically going toward the LSST era. And then Zhao Fan will be telling us about high redshift quasar surveys. And then Paula Kopi will be telling us about results from his large survey as well. So that's, I think, everything for now. And I encourage everyone who's interested to continue attending these sessions. Thanks a lot, everyone, and be safe and take care. Okay.
Thank you.
Bye.